So the next topic is going to be graphing polar functions. So just like in Cartesian, we can graph points, we have curves. You learned an array of parent functions throughout the last few years in the XY plane. Polar has the same thing. There are curves, parent functions, but really we're just going to talk about the attributes of these curves and how you can recognize them based on the function provided. So just recall from the previous lesson that R is your output, and theta is your input. And we're going to start seeing functions, and we're going to see the relationship between r and theta, and they're going to be written to align with Cartesian just so we can get more familiar with them. Okay. So we are going to be using the TI-84 for this lesson. And before we can do that, we have to switch the calculator out of rectangular mode. So you're going to hit the mode key, which is next to the blue second key. You're going to go down to where it says function, and then you'll go over to where it says polar, and then you'll hit enter. All right, once you do that, go ahead and hit y equals. Now you're going to see that instead of seeing y equals, you're going to see r equals, and that's because r is the output. So we're going to input a function where the independent variable is theta, which is given in example 6. So let r equal f of theta. This is the same relationship for y equals f of x. R is the output and theta will be our input, where f of theta is equal to 3 minus 3 sine theta. So I'm going to plug that into my calculator. 3 minus 3, we have our sine, and then theta is going to be the input key, which is the same key as when we plug in x, which is next to the green alpha key. And then don't forget to close your parentheses. And it's a polar function in the polar coordinate system from 0 to 2 pi. Sketch the graph. All right, so we are given a restriction from 0 to 2 pi, just like if we were given a restriction from 0 to 10, we would go to our window and we would type in 0 for the theta minimum, and then for the theta max, it would be 2 pi. So this is a decimal value that I suggested that you remember, the 6.28 decimal. It's standard to go from 0 to 2 pi on its own, okay? And then the step size is standard as well. So something else that you want to do is if we go to graph, some of these are going to be pretty small, some of them are going to be pretty big. So I would suggest going to zoom, and you're going to hit zoom 0, which is just zoom fit. Now if you just hit zoom and hit 0, it'll do it automatically. You don't have to scroll down and click. But now I have a nice window where it fits the edges of my curve so I can get a nice view of it. Now what we're doing is we're going to be taking these thetas, these angles, these input values, plugging them into our function for r and getting an output. That output is going to be the radius for that particular angle, okay? So if I plug in 0, I get 3 minus 3 sine of 0. Sine of 0 is going to be 0, so we end up with 3 minus 0, which is just 3. So when we have an angle of 0, the radius is going to be 3. If I hit trace on the calculator, it automatically puts you at theta is equal to 0, okay? Now, the problem is if we look, we have x equals 3 and y equals 3. My calculator is displaying a polar graph, but it's giving me rectangular coordinates. So to fix that, I hit second zoom, which is format, and I'm going to go over to polar and then hit enter. So now when I go back to my graph and hit trace, now I just see r, which is 3, and theta is equal 0. So there's no having to guess and check, is it x or is it y? It's neither. It's going to, if you were to use x and y, you would have to use the Pythagorean theorem for every single one, which is not efficient, okay? So again, what I did to fix that was I went second zoom, and I moved it over to polar, and then that way I can see what my radius is for each angle. So what I'm going to do is I'm going to plot this at on the grid. So again, the theta is the input, but we usually do the radius first. So I'm going to go out to the circle, which is 3. These circles are weird. Like I have 2 here, which means 1 is like splitting here. So this is 1, this is 2, 3 is somewhere in here, 4, 5 is split, and then 6. All right, so we have a radius of 3, and then angle is 0. So I'm going to plot that right there. All right, and I'm not going to plug in every single angle. I can just trace now. So trace second pi over 6. I have a radius of 1.5. So on my grid, I'm going to extend out 1.5, which it looks like it'll be somewhere like here-ish. And then I'm going to open up to pi over 6. So remember, we have these extra spokes. This is pi over 12, which means pi over 6 will be the second spoke. So I'm going to open up to pi over 6. Pi over 4, trace second pi over 4. I end up with a radius of 0.878. So it's a little bit closer to the pole. So pi over 4 will be the next spoke. So it'll be somewhere in here. So it's going to be pretty tight for now. Pi over 3, second pi divided by 3. I get a radius of 0.401. Which means we're getting even closer to the pole. I'm not even going to try and fit that in there, but pi over 3 will be this spoke, because remember, this spoke is 5 pi over 12. And then pi over 2, just a hunch, because we're getting so close to the pole, I'm assuming it's at the pole. Yes. So at pi over 2, we have a radius of 0. So whenever the radius is 0, you will be at the pole. So just like a curve in Cartesian, we can connect these dots. I started here, and then as my theta increases, my radius is changing based on that theta. So at pi over 2, we are now back at the pole. Now, if you notice, this has symmetry, all right, which means my values after I pass or I bounce or go through the pole are going to resemble the values that I had before I entered the pole. So my first value exiting the pole will be the value that I had at pi over 3, which is going to be the 0.401. And then my 3 pi over 4 will have the same value as pi over 4. That will be 0.878. My value at 5 pi over 6 will equal pi over 6, which is 1.5. And then at pi, we're back to the maximum radius of 3. Okay, so this symmetry occurs for the ones that you will see in this course. They almost always occur 95% of the time. So I'm going to go ahead and sketch those out here. I'm going to start from pi because it's easier to see, and I'm going to do my little ticks as well. So this is 1, 2, 3, 4, and then 5, and then 6 is out here. I guess 3 is not the maximum radius. There's a max radius of 6. So for pi, we're going to have 1, 2, 3. And then let's see, 5 pi over 6 was the 1.5, so I'm going to skip a spoke, because that's family of 12s. So 5 pi over 6 is here. And I might as well go ahead and finish this. This is 3 pi over 4, and then this will be 2 pi over 3. So 5 pi over 6 will be 1.5. So we'll be like here-ish. And then the rest are coming in pretty close. And then we will draw that out. All right, so now we're entering a new realm of symmetry. 7 pi over 6, if I trace 7 pi over 6, I end up with 4.5. Now, if I look at this, I have vertical symmetry. I'm able to fold this on top of itself vertically. If 4.5, if angle 7 pi over 6 has a radius of 4.5, what other angle in this table will have the same radius? 11 pi over 6. So we're seeing that vertical symmetry. So I'm going to go ahead and plot these two together. 7 pi over 6 is going to be here. 11 pi over 6 is here. And they both have a radius of 4.5. So I'm going to go out 4.5. So 1, 2, 3, 1, 2, 3, 4. And I'm going to open up to that angle. Now, I should not have went out that direction. So if it's a positive radius of 4.5, so I'm going 1, 2, 3, 4, and then I'm opening up to 7 pi over 6, just like we plotted in the last video. So that's how I get to the coordinate point, is here. And then same thing for 11 pi over 6, I open up 4, and then I sweep around to get to 11 pi over 6. So we are plotting these points like we did before. This is 4.5. But now as theta increases, we are connecting them to the previous theta. So it was pi and then 7 pi over 6, and then 11 pi over 6 will connect to 2 pi or 0. All right, next we have 5 pi over 4. That will be a radius of 5.121. And then again, that symmetry, 7 pi over 4 will have the same radius. All right, so these angles, 7 pi over 6, this is what, 5 pi over 4? This is 4 pi over 3, just finish those in. And then we have 5 pi over 3, 7 pi over 4. So 5 pi over 4 and 7 pi over 4 will have the same radius, and it is 5.121. So I'm going to extend out to 5, just a little bit past, and then I sweep around to 5 pi over 4. So it'll be just right there. And then 7 pi over 4 will have the same radius. And they will connect. All right. 4 pi over 3. Whoops. We have a radius of 5.598, so almost 6. And then 5 pi over 3 will have the same radius. So almost to 6. So I'm sweeping around again. So 4 pi over 3 is almost 6. Oh, no, it's not. 5.59. That's not almost 6. It's almost like 5.5. So we'll say it's like here. And then these two will connect. And the last one for 3 pi over 2. If I trace 3 pi over 2, I end up with a radius of 6. And that is the max radius. All right, so if I start back at 0, enter, this shows me where I started. I started here. This is where theta is equal to 0. And if I hit the right arrow, it's going to trace around this shape. All right, this is called the orientation, right? And all polar graphs have orientation. In Cartesian, we just read left to right. And polar, they could go clockwise, they could go counterclockwise. It all depends on this function. However, the orientation does not change. So if I'm starting at 0 here, that means it's going this way. It's going to go counterclockwise for the entire curve up until we get to here. Now, if I see this, when I did one complete revolution, it says 6.28. That means my domain for this particular curve is going to be 0 to 2 pi. We only work within one revolution for each of these. Sometimes it could be 0 to pi, but that's going to be on you to determine that by tracing 0 here, 0, and then making sure that when you get back to where you started, keep going, keep going, keep going. I'm looking at it grow. Okay, theta 4.5 point. All right, theta is 6.28. All right, so that's why it's nice to recognize those decimals, okay? Oh, and I guess 2 pi brings us back to 3. Sorry about that. All right, so different shapes. This is called a cardioid, and it looks like a heart, so that's why it's called a cardioid. So we're going to look at these different types of cardioids and what other shapes we'll run into. So graph each of the following. Describe the effect of A and B in the r equals a plus b sine theta. I was going to show a Desmos slider, but because we aren't using, I might use this when we review for the AP exam, but you don't get Desmos for the assessments in this course. Actually, I'll show the Desmos slider when we review for the AP exam, but you only get the TI for your assessment in class, so that's what I'll focus on right now. You'll be able to just graph this. So let's do 3 plus 3 sine theta. I'll just hit zoom 0. So we end up with another cardioid, all right? Another cardioid, but this time it is flipped, all right? Now, because we have 3 plus 3 sine, that means it's going to go around the positive vertical axis here, all right? And if I hit trace, it is going to start here. Theta is equal to 0. And again, I can see that my orientation will be counterclockwise. Okay, so you will get a cardioid when A is equal to B. In this case, A is equal to 3, B is equal to 3, all right? So this results in a cardioid. And it's because it looks like a heart. Now the next case, we have 1 plus 3 sine theta. This is when A is less than B. So we have 1 and 3. And if you type this into your calculator, I have 1 plus 3 sine theta. Go to graph. We get something a little bit different, all right? So now if I were to do a quick sketch of this, if I hit trace, we're starting on the polar axis. Theta is equal to 0. And I can follow this, all right? So I'm in quadrant 1, I go to quadrant 2, and I'm back at the pole. So I'm gonna go ahead and draw that. I go around quadrant 1, quadrant 2, and then I'm back at the pole. When I continue, I go into quadrant 1 with a smaller loop, go through quadrant 2, and then I come back through quadrant 3 to back to where I started. Okay, so the orientation is still going counterclockwise. Zoom in here. It's going around, and then we pass through the pole. It's still going around, and then we pass through the pole again. So what this is doing is it starts here, goes around, passes through the pole again, and then we're back to where we started. So this passes the pole twice, and that's okay, all right? It's not like, oh, it passes through the same point with the same input. No, that rule does not apply here. There are multiple representations for polar coordinates, all right? So this is okay here. What happens here is that we have, I'm probably gonna chop this up. It's called a limacon. It's a C with a little hook under it. I don't know what it's called. If some of you know, let me know. I didn't look it up. A limacon with inner loop. We just call it inner loop usually. Like, oh, it has an inner loop. You're not going to be assessed on that, okay? But that's when the constant is less than the coefficient. Now we have 3 plus 1 sine theta. Go ahead and type that in. Let's do zoom 0. 3 plus 1 sine theta. That might, oh, that's why. Whoops, that should be a 1, not a 4. So zoom 0, there we go. Okay, so this one, it's not exactly a circle. It's a little stretched out. If I trace, we're starting on the polar axis again, and it's going to open up counterclockwise and go all the way around. So we're going to go up, and it kind of flattens out at the bottom, and then it comes back to here. So orientation is still counterclockwise. This is where theta is equal to 0. So this is when the constant is greater than the coefficient. This is called a beam. So if you look at all three of these, all three of them, that the constant and the coefficient change, but it's sine. Sine will have, oh, what's that notated? In polar coordinates, equations involving sine functions are generally symmetrical with respect to the line theta equals pi over 2. So when you have sine, it will have vertical symmetry. And this is going to be important because you're going to have to recognize these in the future. Now we have the same functions, but they're in cosine. Without even plotting it or putting it in the graphing calculator, if I have 3 plus 3 cosine, that's going to be a cardioid because it's A is equal to A, but now it's going to have horizontal symmetry. And since it's plus, it's going to be around the polar axis. So if we type it in, I have 3 plus 3 cosine theta, graph it, zoom 0, hit trace. We are starting on the polar axis, and then the orientation is going to be counterclockwise again. So I come around, and then I bounce, and I come back to here. So it looks just like the sine one, but now instead of having vertical symmetry, this has horizontal symmetry. And this is another cardioid. So now without graphing it in a calculator, if I wanted to graph 1 plus 3 cosine theta, I'm going to start on the polar axis again. So theta is equal to 0. But now the inner loop will happen in quadrants 4 and 1 instead of 1 and 2. So I'm going to go around. I pass through the pole, pass through the pole again, and then I come back to here. And the orientation will be counterclockwise again. So again, that pathway is I start here, I come around, pass through the pole, pass through the pole again, and then I'm here. And again, you'll have the calculator at your disposal. If you're like, I will not remember this, that's okay, all right? So you can graph it here, trace it, and then you can trace it along and see the pathway it's taking. And it ends at 2 pi. And then we have our bean. So with this one, we'll start, and we're going to start on the polar axis again. And then the bean, instead of being a little flat on this portion, it's going to be flat on this portion, okay? So it's going to go up, it's going to flatten out a little over here, and then it finishes out back to where it started. If you need to see that, we have 3 plus 1 cosine theta. We'll do zoom 0. And you can't really see it like this. If you do zoom square, so zoom 5, you'll be able to see it better. So you see that it's more elongated on the right side than the left side. That's what's happening there. That's why we call it a bean. So on polar coordinates, equations involving cosine functions are generally symmetric with respect to the line theta equals 0 degrees. All right, next we're going to have some petals. Each of the following describe the effects of A and B again. So again, go to your calculator. Now we got rid of the constant, it's just the coefficient, and now we have a new one on the inside. So we'll have 2 sine of 2 theta, zoom 0. And now we have something going on. There's no more cardioid or limacon or bean. Now we are dealing with petals, okay? So when we get rid of that constant and we add a coefficient with the theta, we are dealing with petals. So if we trace, I'm starting at the pole now, okay? And if I hit the right arrow, I'm able to see the orientation and how it travels. Now, if we do this first petal, I come around and I'm approaching the pole again. Look where it goes. Notice where it goes. I go from quadrant 1 to quadrant 4. It is a smooth curve. In order for this to go through to quadrant 2, it would have to be a sharp turn. To get to quadrant 3, we would have to change the direction that we are traveling, all right? So this is going at a consistent curve as we pass on to the next petal, okay? So I pass on into quadrant 2. I come back to the pole. Now, same thing. If I were to try and go to quadrant 2, I would have to make a sharp turn, all right? Or change my direction. But instead, I'm going to end up in quadrant 3. So I go to quadrant 3, continue the curve into quadrant 4, and then I'm back to the start. So we pass the pole, we start there, theta equals 0 at the pole. I come around, I pass the pole once, twice, 3 times, and then I'm back. That's okay, okay? So this is the first petal, this is the second petal, third petal, fourth petal. And what's happening is that this is going to be your max radius is 2. So in these petals, each petal has a maximum radius of 2 because of that coefficient. The coefficient on the inside, that tells you the number of petals you will have, okay? So that means for this one, we're going to double it. That means because we have 2 theta, that means we have 4 petals. Now, if we compare this to cosine, if we do 2 cosine 2 theta, it changes. It's rotated a little bit. Let's do zoom 0. So now, instead of the petals being inside of the quadrants, they are now along the axis, all right? So if I hit trace, I'm not starting at the pole anymore. I'm starting on the polar axis. And that's because cosine theta on the unit circle, if we think of the unit circle over here, for 0 degrees, cosine is 1, x equals 1, and then sine is 0. So that means sine is going to have a radius of 0, which is at the pole. Cosine would have a radius of 1, which is on the polar axis, okay? So with this one, If I hit trace and I follow it, I'm still following the same trend, no sharp turns as I pass through the pole. So I'm starting my first petal. It won't complete until the end. I go to around this axis here, come around. Now, the only next choice I have is going along the negative horizontal and then smoothly going to the positive vertical back through the pole to finish the last petal. All right, so the orientation is still going around this direction. And again, every time it passes through the pole, it is a smooth turn. It's not choppy. It's not bouncy like the cardioid up here. Okay, so one more time, we start at the pole, come around. It's a smooth turnaround through the pole every single time. And then we finish that last petal. So again, we have a maximum radius within each petal of 2. And then because it has 2 theta, it has 4 petals. All right, this next one. So now we have 3 sine of 2 theta. So this is the same as the previous one, but now we have a 3 instead of a 2. That means your petals are going to be larger. All right, so now they're going to have a radius of 3 instead of a radius of 2. But it's going to follow the same trend. So if we come back to our sines, I have 2 sine 2 theta and then 3 sine 2 theta. Let's do zoom 0. So the blue one was the first one we did, and now the red one is the second one with the radius of 3. So if I hit trace, they're both starting at the pole, and they both have the same orientation. And then lastly, so this one has a max radius of 3. This has a max radius of 2. And because it's 2 theta, it has 4 petals. So if we look at this last one without even putting it into the graphing calculator, we're going to have 4 petals. It's sine, so it's going to start at the pole. We're going to start in quadrant 1. It'll smoothly go through the pole. Actually, let's make the petals bigger. Woo! And we're back to where we started. So this has a maximum radius of 4. And if you were to plug that in, we get 4 sine 2 theta, 5 theta. So we end up with this. Whoops. There we go. And the same thing would happen with cosine. If you were to graph this, we would still start on the pole, but now it's going to be larger. So we come up, pass down, smoothly through the pole. So this one has a maximum radius of 3, and we have 4 petals because it's 2 theta. And if we were to switch over to 4 cosine 2 theta, we have a max radius of 4. And the petals do get larger as the radius gets larger. So this has a radius of 4, and 2 theta means 4 petals. So when we increase the first coefficient, it increases the radius, therefore the petals get larger. It does not change the number of petals. So let's go back to the original. We have 2 sine of 2 theta. It's sine, so we're starting at the pole. 2 theta, so we have 4 petals. So I'm going to go 1, 2, 3, 4, boom. All right, so this has a max radius of 2, and 2 theta means 4 petals. So now let's look at the next one. Let's think of 2 sine 3 theta. 2 sine 3 theta. If we follow the pattern from the previous one, it doubles. That means we should have 6 petals, but we don't. Okay, so we kind of lose our pattern here. All right, but I'm looking at sine. Hopefully I still start at the pole. Yes, so we're still starting at the pole because it's sine. So theta is equal to 0. And we do still have vertical symmetry. We are able to fold this vertically and have it overlay itself. So if I follow this orientation, I have that first loop in quadrant 1, and then we go along the negative vertical axis, and then we finish in quadrant 2. Okay, so I come around, I go down, back up around to here. So this has a maximum radius of 2. But now that we have 3 theta, this means 3 petals. So that throws a wrench in my plan. Now, if you're seeing that your petals are getting choppy, like linear, go to your window and then change your step size. So put like 0.001, make it smaller. It will take longer to graph, but it does smooth it out. So again, that is your, if you go to window, it is your theta step. Make it smaller so that way, oops, too much. Don't make it too small though, because it looks like 0 to the calculator. So maybe 0.001 and that'll smooth out the curves for you. All right, so then let's check out 2 sine theta, or 2 sine 4 theta. So is it 4 or 8? Okay, so zoom 0. Looks like we get 8 petals. Come on, you got it, calculator. So I'm not even going to try and follow the curve for this. I see that it has 2 petals in each quadrant. So I'm going to do 2 petals here, 2 petals here, 2 petals here, 2 petals here, okay? And they each have a maximum radius of 2. So if I have 4 theta, that means I have 8 petals. Okay, so this pattern is that if the coefficient with the theta is even, it's doubled. If the coefficient is odd, it stays the same, okay? So if I were to type in 5 theta, we would go back down to 5 petals, which that should make you think of complex, like when we take the complex roots, or the root of a complex number, this would be to the 5th root. So we get 5 complex values evenly spaced, all right? So that's the same idea with polar. And if we go to cosine, graphing these, we already know what 2 cosine 4 theta would look like. We have 4 petals, and each petal has a maximum radius of 2. Now, if I go to 2 cosine 5 theta, we're going to have 5 petals, but it's going to start on the pole again, all right? So again, I'm not going to try and follow this. I'm just going to draw my 5 petals. There's a petal, petal over here, petal over here, petal over here. And then if we do 6 theta, it's going to start on the polar axis again, but now we will have 12 petals. So it looks like we have a petal on each axis. And then I think there are 2 in between each. Yes, so 2 here, 2 here, 2 here. Oh my gosh, 2 here. And then we have our 12. All right, so 6 theta means 12 petals. So you are never asked to sketch these. You will just have to recognize them. But learning how to sketch them won't hurt because you have to do it next year if you plan to take calculus. There's a couple notes at the bottom, so just make sure that you read through that. Hope this helps.